Right, a very good morning to you all. Welcome to this session, optical fibers. All right, this is sort of
And
an in-between session, uh, summarizing the first batch of the videos I gave you, videos 1 to 9. I think by now everyone is done. You know how we operate, Magatora nodes, and O and O. Today we'll be resuming. I'll be asking questions. Right. Introduction. Uh, Page 1. I think to begin, let us start with communication. What is communication? What is communication? What is communication? Ndakamira mimi. Beso sandakatanga kubvunza izvozvo pavideo. I think I started with communication. What is communication? Transferring of information. So transferring of info from a point A to point B. What I am doing right now, I'm communicating with you. I'm transferring knowledge from point A to point B. Basics. That is communication. Right. How is that done? I think from fundamental. Yeah. Vanadoti tanoisi muri kubuda ndiani gwara chief ndokubudisa again. Mute account yenyu please. Right. Transferring info from one point to another. All right, different ways to do that. And I was saying from background in your fundamentals of telecommunications, you got into ways how you can transfer information from one point to another. In Nini, I'll be dealing with how to do that using medium in the optical fiber. I think the channels they differ from we have the atmosphere, my electrical lines, optical fiber, any other channels, you know. Any other channels, you know. I need to respond. Any other channels, you know. Atmosphere, electrical lines, optical fibers. I'm stuck. I'm waiting for a response. Right. Philip Mugabe trying to answer, but network yagadab. Anyone to respond and the network is now. What is a channel? Okay. What is a channel? Abitania, what is a channel? We don't animate too much.
so, channel is a path.
A channel is
a path.
Path.
The path that conveys information.
A path that conveys information. A channel is a vehicle for transporting information. If I want to transport a message, what I use to transport that message, that is what we call a channel. It seems no one else has examples of those channels. Let's go into, all right. Modulation. Assume the knowledge. You're supposed to know this is what up in them course here. What is modulation? You have two types, analog, digital. You are familiar with amplitude modulation. You are familiar with frequency modulation. Phase modulation, I don't know O, but amplitude and frequency modulation, you are supposed to know what that is. On the digital side, you are supposed to know digitalization. Digitalization. This is not supposed to be something new for you. For now, you're supposed to know. You're supposed to know what is digitalization. Basically, the sampling and quantization. Why is it necessary to know digitalization? Because when we are dealing with optical fibers, modulation, the type of modulation that happens, it's your transmitter. There's modulation that happens at the transmitter. It deals with digital signals. All right. What do I mean by that? I think to explain that, we're going to explain the block diagram. The block diagram. Right. You need to know this. Remember my videos, block diagram. From the block diagram, we have the message, we have the light source, we have, what do we have here? Battery. We have the optical detector. What do we have?
Media.
We have our channel, the media, we have the optical fiber. What happens at this point? There is digitalization, somewhere at this point, digitalization. An electrical signal is turned into a digital signal. A digital signal 101010 at that point. Then when this signal interacts with the light source, then we have the light source switching on and off, on and off, on and off, corresponding to this. Those on and offs, they go into the optical fiber, and that is how information is transported from a point A to a point B. Details of this is in the session video. You need to understand the block diagram of an optical telecommunication system. And there it is, in simple terms. We have the message. Can always also read, if you want to get more marks in exam, you can put my transducers up or my input transducers. Or the output, what do we have? On the input, we have a transducer. On the output, anyone knows that teach you know it on the output. What is a transducer? But when telecommunications, that is what you're supposed to know. Transducer, there's a transducer somewhere here. Transducer. Chief, we are all interacting. What is a transducer?
It is a device, an electrical device that conveys information to electrical form, vice
Thank you
versa.
very much. Thank you very much. Conveys any form of energy into electrical. So block diagram, exam, that is definitely 6 marks. What you need to know, pan a message, pan a light source, pan a channel, pan an optical detector, then you have a message at the receiver here. This is the transmission, and we have the receiver on the other side. Detail is up to you doing as one detail. You need to know each of the elements of that block system or block diagram, from the message. How does the message, which form of energy is the message? In my example, it's the voice. What happens? The voice in the transport by array. In what form is it being transported? By light source up. What happens by light source? What form of modulation happens there? Then Rapinam channel, how is it transported? That is the type of thing, you know. When it gets to the optical detector, how is it received? You understand? Those are the things you need to know. Plus Google, you fill in the gaps. You fill in the gaps, and that is learning. Right. For a high quality and reliable communication, there is need for 2 things. High quality and reliable communication, there is need for 2 things. SNR. What is SNR? Anybody? The right things.
Signal to noise ratio.
Thank you very much. What does it signify? Canary high, what does that mean?
I think if it is high, we have quality signal.
If it is high, we have quality signal. Thank you very much. All right, quick question. All right, high signal to noise ratio, it means you have a high quality of your signal. The same way you're listening to my voice as I speak here, it's more or less the same thing you are hearing on that side. Why? That is high signal noise ratio. If it is very low, you won't be hearing me clearly. You need to understand what signal to noise ratio is. Obviously, there is something big than Santango Towers. We need a higher bandwidth for a high quality and a reliable communication. What is bandwidth? Control tolerance bandwidth. What do we mean? This is a discussion on God Tower Run. Unmute yourselves. Jatanga usama participation marks up.
Bandwidth is the channel capacity.
Channel capacity. Layman terms. Channel capacity. When you talk of the channel capacity, what is that?
Bandwidth.
Taura enyu, madam. Taura enyu.
Bandwidth is the difference between the upper and the lower frequencies. That's the channel capacity as well.
Okay. Difference between the upper and the lower frequencies. What does that signify? If that range is big, it means you have a quality communication system. If that range is big. Frequencies, bandwidth, these are just frequencies. F min, F max. If this difference is very big, 2 gigahertz, bandwidth, 2 gigahertz, 20 gigahertz, 20 gigabits. I mean, if that difference is big, it means you have a quality telecommunication system. So I'm not on gigabytes per second, 20 gigahertz. What is bandwidth between these two? What is this one as gigabytes per second? Well, let me start with that I'm not saying. What is 20 gigabyte? What is that? What is 20 gigabytes per second? I feel it's necessary to define as units. What is 20 gigahertz? What is bandwidth between those three? Between those three, 1, 2, 3, what is bandwidth?
20 gigahertz.
Yes.
20 gigahertz. And gigabits per second, what is that?
Yeah, that's bandwidth.
20 gigabytes per second. That's bandwidth.
That's the speed
Thank
of
you very
transmission.
much. The speed of transmission and 20 gigabytes. This is our bandwidth. You are supposed to know that. I'm an engineer in telecommunications, and you cannot differentiate those three. That is the type of stuff you are supposed to know. All right. Someone at 20 gigabytes here with the chair. I'm not going to put much effort into that. All right. You need high bandwidth to have communication system inequality. Why? Data, all we needed was maybe to transmit a voice signal. Data retrieve voice ichi. Data retrieve voice. That is your amount of bandwidth, they can want a voice signal. My telephones. 300 to 3,000. Jana Narizia. This one.
I think 8 kilohertz.
Ichi
48.
Ichi 48. 48.
4
kb.
4 kb.
4 kb. Someone verify that. Voice. If I want to transmit a voice signal,
4
how much bandwidth will I need?
Yes, it's 4
4 KB.
it's 4 KB. Yes.
Around that bandwidth, around that much, 3 KB to transmit a voice signal. But easy. You are no longer doing that. Only that. We are no longer doing only that. We have my channel is a data transmitter, voice, data, video, images, and a TV papapo. Zvinosvika 20 gigabytes. But how can you transmit 20 gigabytes using a channel, maybe Rene bandwidth 4 kilohertz? How can you do that? It is no longer possible. Low bandwidth. This is low bandwidth. You cannot transmit this amount of data using a 4 kilohertz channel. What does that mean? It means we need more channels and a more bandwidth to cater for this amount of space. We need more channels and more bandwidth to cater for this amount of space. More bandwidth channels which do that. We obviously have introduction in my fibers. All right, now but that's a spectrum. We have what we call the spectrum of the electromagnetic spectrum. My optical fibers, they offer how much frequency range in my optical fibers, the bandwidth. What is the bandwidth? Yeah, my optical fibers, right? 1 gigahertz coaxial cable. What is the bandwidth for my optical fibers? The range of frequencies which the optical fibers operate. I don't want to ban up 30 terahertz. Is that true? Bandwidth optical fibers. Someone respond to that. Whenever Google. All right, bandwidth optical fibers, 10 giga per second. What is that? 10 gigahertz. Bandwidth optics, 10 gigabytes per second. 10 gigahertz. I think it is much larger than that. Okay, here and corner 10 gigahertz. Optical fibers obviously offers more bandwidth. It means with the increase in demand here, data rate increase in my data rate, it means my optical fibers can cater for those demands. That is one of my main reasons why we have introduction in my optical fibers. Obviously, there are more reasons why optical fibers. This is the question for the exam. Why use optical fibers? Besides offering more bandwidth, there are other reasons why we use my optical fibers. Someone to help exam. Why do we use optical fibers? Any other reasons? Why use optical fibers? Unmute yourselves only if you want to respond. After that, mute yourselves. Apanado respond. Why use my optical fibers? Zero more videos.
They're less bulky. They're lighter.
Less bulky. They are lighter. Those are some of the
They
reasons.
carry more data.
They carry more data, more bandwidth, higher data
have-
rates. They have
They can work in
No
any
magnetic interference.
low EMI. They can work in
environment.
No magnetic interference.
All right, electromagnetic spectrum. You need to understand the air bandwidth. You need to understand the electromagnetic spectrum. I think it's there in one of the videos. I cannot pinpoint my figures actually exact. That's why I have to leave it for you. You need to understand the electromagnetic spectrum. Those near Pama frequencies up. Wait. All right. Let's move on to structure of optical fiber. Introduce the structure of the optical fiber. Introduce law. Structure of the optical fiber. The optical fiber is made up of the core. It is made up of the cladding. Those in the bases. We have the core and the cladding. Outside this, obviously, there is another layer for protection. Let's call it a shield. I don't know if it has another name. There is another layer. I don't care much about this layer, which protects the optical fiber. I care much about the core and the cladding. This is the structure of the optical fiber. It is the core and the cladding. All right. These two, they have what we call the refractive indices. Okay, refractive index into a refractive index. Definition, refractive index is N1. This video is known for one of our videos, ever before. Right, refractive index, what is that? I'm sure there's wonder. Makawana wa videos here. Unmute yourselves, everyone. Unmute yourselves. Chabaiwa, Chikwamba, unmute yourselves. Makawana ma videos here. ASR9. But the refractive index,
It's a,
but
it's a
any magamona.
it's a number that describes how fast light travels through.
And I thank you very much. A number which describes how fast light travels in a medium.
Through a
Well, through a medium. I think basically that sums it up. Thank you very much. That is a very good response. The refractive index N is equal to C over V, where C, what is C? This is the speed of light. Speed of light. I'm still respond. Unmute yourselves. Can I still respond? Speed of light in a vacuum, in free space. That is C. And what is V? That is the speed of light in a given medium. So if our medium refractive index of N1, it means V is V1, the speed of light in the medium 1. The refractive index, it is the ratio of the speed of light in a vacuum in free space and the speed of light in a given medium. You're supposed to know that. So the refractive index is just a ratio. It shows with the light say in a medium. Can I repeat? All right. The refractive index is just a ratio. It's a number which allows us to determine what is the speed of light in a given medium. If I rearrange this, I can put it as V1 is equal to C over N1. So if I'm given N1, which is the refractive index of medium 1, I can calculate the speed V1 of light in that medium. I can calculate the speed of light in medium number 1. Basically, this is what it is. It leaves us here. V is equals to C over N. So this number, it obviously defines the speed of light in that given medium H, where C is the speed of light in a vacuum. And then you have the refractive index. So the refractive index of our core, we have N1, and the refractive index of our cladding, we have N2. Those are the values we are going to be using until infinity. N1 refractive index of core, N2 refractive index of cladding. My exam, N1, N2. I won't tell you with the refractive index H. I'm telling you now. N1 is the core, N2 is the cladding. My sources, I'm gonna go vice versa, and my N6 or my N7. My sources. And I use N1 and N2. So this is the structure of optical fiber red. We have the core and the cladding. They have my refractive indices. Index. Sienna. Which one is bigger? Diana, Gianna, stop answering my questions. Anyone else? In fact, when we hit in a 1T, the Muruk answer my questions only. All right. Between the core and the cladding, which of the two has a higher refractive index? Unmute yourselves.
Course.
Why? The core has a higher refractive index. Why?
For total internal reflections.
Yeah. Diana Tauro.
Emmanuel.
Emmanuel. Stogo. Right. The core is a higher refractive index. Or so let me put it like this. Why? To effect total internal reflection, N1 is greater than N2. You later on see that N1 is approximately equal to N2. We'll discuss this situation later on. And that is it for the structure of the optical fibers. Running out of time, 10 minutes. All right, introduction of Snell's law. All right, there is obviously a lot of things in between these interpreters. Like in between introduction, electromagnetic spectrum, what is bandwidth and all, kuskapa structure apa. A lot of things for you kuti mbate ndo pamunoenda muchinoverenga muchinotsvaga paGoogle. My books, I cannot obviously advise you for my books by name because my book I'm gonna do my share. By internet, my books which deals with purely optical fibers. I think got complicated. So I get to my notes, and we build on that. And I'm asking how level I'm researcher. Most people are those big books. Because for me, they were very confusing. And I'm hoping you avoid that as well. Build up on very small things. To my notes, to my Indians, for my YouTube and all, you build on that. Put in a background like a Simba. Then you go on, this is a bit more complicated. Right. I was saying in between, there is need to add some beef to the skeleton. That is learning. But obviously, most of the things Roma videos angle, those in room exam. But understanding at the same time is very important. All right, Snell's law. Takaita first introduction to fundamentals of telecommunication fundamentals. We did Snell's law. And to summarize, N1 sine theta 1 is equals N2 sine theta 2. That is all I have to say about Snell's law. Introduction of TIR. What is TIR?
Total internal reflection.
total internal reflection. This TIR is very crucial for transmission message using optical fiber as a channel. I really believe total internal reflection. This is what keeps light in an optical fiber. Total internal reflection. Proper definition. When I got proper definition, what is total internal reflection? Technical definition. Total internal reflection. Total internal reflection. What happens? Something to do with the critical angle. Definition. What is the critical angle? Somewhere. What is the critical angle?
Critical angle, it is the angle, the smallest angle below 90, smallest angle by which the light can strike the co-cladding boundary and still propagate within the optical fiber.
Thank you very much. Critical angle, angle of incidence. Angle of incidence, if you have a boundary, angle of incidence which produces refracted ray, angle 90 degrees. Layman terms. So that one accommodate our, that is a proper definition. Optical fibers. A lot of you won't even understand that. What you understand, incident angle, which produces 90 degrees on the other side. For the rest of you. Can I tap for that smallest value? What happens? For that smallest value, and by definition, the smallest value, which produces 90 degrees refracted ray. What happens when that angle is bigger than your smallest value?
Refraction.
What?
I think you want your total internal reflection. I think about the refraction.
Total internal reflection. Okay. Quite a refraction. Total internal reflection. Right. If we have a boundary, 10 minutes. If we have a boundary, this is our boundary. No, let me do this. There is our boundary there. This is my incident. Incident ray. So, then is refraction. Refraction. Wanda rangu deripire. This one. Doji. Reflection. Reflection. All right. Angle of refraction angle can 90. This angle E, you go up. Do ya 90? You got that. Then angle gunok. You get up. This is my boundary normal. You get up. Do ya critical angle? I hope I'm not missing something. This is the critical angle when this refracted ray can arrive at 90 degrees here. Then angle E can go increase. Angle E up. Then we have total internal reflection. Be very careful, comrade. Right. So that is total internal reflection. I need a proper definition. It will probably be in in-class test or an exam. Critical angle, Snell's law. You need to know those things. Definitely you are going to meet them more exam. Right. Critical angle, there is an equation for critical angle. You know, the sine phi is equals to n2 over n1. You need to know this equation. You need to know that equation. Irimo, my videos. You need to know how it is derived. and all that. Like 2 minutes, 42 seconds. Any questions so far? Any questions so far? Nope. We are done here. Join me soon after.